So if we have a vector valued function that gives us the position of a particle at any point in time, then a logical next question might be, how might we quantify the velocity of that particle? If I have a vector value function that provides us with position, and I want to figure out velocity, well, as you might expect, since velocity is the rate of change of position, we're just going to find the rate at which the x component is changing with respect to time, and also the rate at which the y component is changing with respect to time, and we get a vector. We get a new vector that's going to be the velocity vector. Now, remember that it's always been the case in this course that our velocity has been a vector. The only difference is we were stuck in 1D. In other words, we were stuck in a line. So we only had two dimensions, right? Left and right, positive and negative, up and down, right? So we didn't have to worry about having two different components. We just had to worry about whether our velocity was positive or negative. Now we've got this new dimension, this new degree of freedom where we can start going in all sorts of different angles on the plane. But we still have a magnitude and a direction. And just like before, just like old school stuff, the magnitude of the velocity is still the speed. Remember, we used to just take the absolute value of the velocity and said, oh, well, that's the positive version of the velocity. Whether the velocity is positive or negative, we just throw away the negative, we get the speed. Well, that's kind of the same thing we're doing here, but we can't just throw away the negatives. When we find the absolute value of a vector, we're actually finding its magnitude, or we're finding its length of the arrow, right? So we use the distance formula, aka our favorite formula, the Pythagorean theorem. It's the same thing, prettied up. That's not how you spell theorem. Theorem, there we go. All right, so to find the velocity function, we take the derivative with respect to time of the x and the y positions, and we just leave it in vector form. We leave it in component form. If we wanted to find the speed of the particle at a given time, that's not going to be a vector. That's going to be the magnitude of the vector. It's going to be a scalar, a numerical answer, not an x comma y, just a single number. And we would do the square root of x prime of t squared plus y prime of t squared. And if we're interested in any particular value of t, we can find its speed by just plugging in that value. Okay. One thing I guess I forgot to put in here, and maybe it's because it doesn't show up that often, is the direction. Remember that magnitudes and directions are embodied in this vector. To find the direction, we have to find the theta value, which is the inverse tangent. Actually, let's write it this way instead. We'll take the tangent of theta, and that's going to give us the change. Oh goodness, the change in our y speed with respect to the change in our x's speed. Interestingly, the slope is y over x, and that gives us the slope of the tangent line. Gasp! It all comes together. So yeah, these are two important formulas. This one's probably going to be the one that's used more often. This one does show up from time to time, but is not quite as common. Alrighty, so let's go back to our friends, our two position functions that both created that fun cubic graph. Remember that these two particles are traveling the same path but at different speeds. Given the position, find the corresponding velocity vectors. So let's take a look at this. For P1, we have V1 is going to be, it's as simple as two baby derivatives, right? The derivative of 2t is 2. The derivative of t cubed is 3t squared, and negative 4t for the negative 2t squared. That's it. That is the velocity vector. There's nothing else to it. It is the vector that represents the x and y components of this particle's velocity. V2 of t is going to work the same way, clearly. We'll have a 4, and then we'll have 24t squared minus 16t. All right, great. So we know that each of these particles passes through the point 2, negative 1, or if we don't, we can show that they do by figuring out the t-value. So for example, if x equals 2, then t equals 1 for this guy. And if t equals 1, then y equals 1 minus 2, or negative 1. So 2, negative 1 checks out over there. So we can figure out the velocity vector, v1 of 1. Okay, that's our input value, is the t value. And the x component is constant at 2. The y component has a t in it, so we'll plug in t equals 1. We'll get 3 minus 4, we'll get negative 1. 2, negative 1. Well, that's a little surprising, but trust me, it's just a coincidence. The location and the velocity don't always match. It's just a complete coincidence that they'd happen to here. If we do the same thing over here, first of all, make sure it goes through the point 2, negative 1. Of course it does, because we already discussed how these follow the same path. But let's just, for fun, let's set x equal to 2. And actually, it's not for fun. We need this value, right? We need to figure out what the t value is. So if 4t equals 2, then t equals 2. Notice that it's a different t value to get that point, because they're not traveling to each of these points at the same time. That's the whole point of this exercise. So if the t value equals 2, then we can find that the y value, in fact, equals, oh gosh, I don't know. Let's factor out an 8t squared, then we'll get t minus 1. So then the t value of 2 gets subtracted by 1. So when we just, there's something going wrong here. You know, sometimes I might learn that it's best to work these out before recording them, because this is not right. If x equals 2, then x equals 4t equals 2 means that t equals 1/2. All right, sorry about that. So that means that when we plug in a 1/2 into here, we get t times 1/4 times 1/2 minus 1 is negative 1/2, and that's going to give us negative 1. All right, so that was actually not a waste of time to do that, because it found my error, my unintentional error. Anyway, so we found that the t value is 1/2 for this one when we're at the desired location. So we'll do v2 of 1/2. Now our velocity function for this one is 4, which is a constant, comma. Let's see, so we're going to plug in 1/2 for t. We're going to get 1/4. 1/4 of 24 is 6. 6 minus 8 is negative 2. All right, so there's our velocity vector at the same point, but following this different position function. All right, fantastic. So if we're asked for the velocity vector, we're done. Now, one thing we might want to try to understand is what's different about these and what's the same. Okay, so spend a little bit of time thinking about this, and hopefully you realized that this is 2 times the other one. Okay, so the magnitude is twice as big on the green one than the red one. So the magnitude of v1 of 1 is the square root of 4, which is 2 squared, plus 1, which is negative 1 squared, is the square root of 5. So whatever units they happen to be, this would be meters per second, feet per minute, miles per hour, whatever it might be. We can go ahead and work out as well that the magnitude of the velocity for the other one works out to be 2 times the square root of 5. So that's how they differ. As we've already talked about, the second one is going twice as fast as the first one. But there is something that is the same about these, and that's going to be the direction. You'll notice that that both are traveling. Both are traveling along the same direction. Along the same, I'll call it a slope of rise of negative 1 and run of 2, because negative 2 divided by 4 is the same thing as negative 1 divided by 2. And tangent of theta equals negative 1/2. So our direction is theta equals inverse tangent of negative 1/2. And if you want a calculator, or you want a decimal value of that, you put it into a calculator, because this is not a value that I personally have memorized. One thing to double check is, do we have to flip this around? But in quadrant 4, we don't need to add half a rotation. Inverse tangent gives us answers in quadrant 1 and quadrant 4. So we're good with that. All right, so the same direction, different magnitude with these guys. All right, so one nice thing we can do is we can visualize this. We can watch these paths, the slower one and the faster one, get generated, along with their tangent vectors. Their velocity vectors are going to be tangent to the curve, so you can type those in, or you can just follow along here. And when I push play on this one, we can watch as our velocity vector changes in magnitude and direction. Notice that the magnitude is shrinking because it's slowing down. And the direction is changing because the direction of the path is changing. It shouldn't be surprising that the direction of the path is the line tangent to the path. That's what it means. All right, so it took a long time for me to fill in the gaps to watch that one create. But now if we look at this one that goes twice as fast, well, look at that. It goes twice as fast. That's fantastic. All right, so we can kind of see how changing the components is going to affect not necessarily the shape of the path, but the speed at which the path is following. So on this faster one, we found that t equals 1/2 when we're at the point 2, -1. And the slower one, we found that that was when t equals 1. Okay? So take a look. We're at the point 2, -1 with a magnitude of 2.2 and a direction of -0.46 radians. Okay? Notice that we double the magnitude, but we have the exact same direction on the faster one. Okay, so this is the fast one, and this is the slow one. Same direction, twice as big of a magnitude. And that 4.5 is 2 times the square root of 5 that we just calculated.